mechanisms. So let's just look at one example very briefly. So here we have the decomposition of ozone, which is another environmental issue that you will be faced with in your lifetime. So this is the overall reaction, and you can't use the stoichiometry to figure out the order of the reaction, but if you divide it up into elementary reaction steps, then you can use the stoichiometry to write the rate law for each step of that reaction. So the first step here is a unimolecular step. You have one thing going to two things, and molecularity is the number of reactant molecules that come together to form product. So unimolecular, you just have one thing that's forming some kind of product. What do you think it's called if you have two things forming a product? Bimolecular. These are good little 1 or 2 point questions on a test. They're not very, very hard. They should be pretty easy to think about. So we have unimolecular. Examples would be some kind of decomposition or radioactive decay. Bimolecular, two reactants coming together to form products. And termolecular is three reactants coming together to form a product. And that's rare. And you can remember that it's rare if you think about how you would hold 3 tennis balls in your hand and have them all come together at the same time to form product. That is a difficult thing to do. Two things coming together is easy. Bimolecular is very common. Termolecular, not very common, that they all come together at the same time to form a product. All right, so we can write rate laws for each step here. For the first step here, the rate would be equal to a k. I don't have the k written up here, but there's always going to be a little k over the arrow. So k times the reactant would be here. For bimolecular, again, assume a k over there. What's that rate going to be equal to? Okay, let's just take 10 more seconds since class is almost over. Yep. So it's this one right down here. Oops. So we have the rate is equal to k times these two reactants. You can sum up the steps and get the overall reactants. Notice that O is an intermediate. It's formed here, decayed here. It goes away. And so O doesn't appear in the overall expression. So we're going to talk a lot about reaction intermediates next time. And also remember that you can't prove reaction mechanisms to be correct. They're just consistent with the data that you have.